Hello everyone, nice to see you. So let us recall our previous discussion. It was quite long time ago. So we introduced the concept of geometric optics, and if we have uniform medium with constant optical properties, how ray of light is traveling in this medium without any interfaces between two different medias. The ray of light is traveling straight and it deflects from the straight trajectory only in that case when there is some change of optical properties of the medium or there is interface between two medium with different optical constants. Which optical constants you know, which describe interaction of light as electromagnetic wave with the material of the medium? Refractive index. Refractive index. So refractive index, what is this? How we define it?
C over lambda. C over velocity of light.
So we need to know C is a constant parameter, it's speed of light or propagation of electromagnetic waves in free space, in vacuum. But because of interaction with the crystalline lattice of some material, for instance, or just atoms, if we have some gas or liquid, light or electromagnetic waves travel in this medium with lower speed than speed of light in vacuum. The ratio between speed of light in vacuum to the speed of light in given material will give us refractive index. Is refractive index a function of wavelengths or not? Is it constant material, like constant number for like property of the material as a constant number, or it depends on the wavelengths?
It's constant. Depends on the material.
Well, if you consider monochromatic light, then you may say that it's constant. However, n is a function of wavelengths because we have this dispersion. If you consider a prism made of glass or some other transparent material and let a white light pass through this prism, because of so-called dispersion, this light will split in different colorful fringes. So it will represent some spectrum. Why it happens? Because the same material possesses different values of refractive index for different wavelengths. So that's why we kind of refract at different angle, different wavelengths, and eventually we get this spectral distribution of white light. So this is a function of wavelengths, and if we want to specify and consider refractive index as a property of the material, then we need to claim that spectral distribution, the spectral dependence of refractive index, in that case, as a spectrum, this is a unique feature of the material and it will be always different for every material depending on its chemical and composition and structural properties. So there is another parameter we mentioned also about this Lambert-Boer law. So you remember what is that? It's absorption of light, how light intensity decays as light travels inside the material. So exponential decay. So we have I naught times exponent in the power of minus alpha x. I think we discussed this. So this alpha is the absorption coefficient. And absorption coefficient is a feature, also a spectral dependence, is a feature how light is absorbed by the material. So you have two parameters. First of all, refractive index, and another is absorption coefficient. So these are considered to be optical constants, which define how light or any electromagnetic wave interacts with the material in terms of reflection and absorption. Because if we have some like sample of some material, we shine light, there is some incident light intensity on the surface of this sample, then what happens? Part of this light is reflecting, so we consider this reflection law. Then part goes inside the material, and obviously, if it goes through the material, it is absorbed. So if we consider it as a flux of photons from particle point like nature of light, then number of photons is decreasing per unit area per unit time, this flux, because of absorption. So there is some absorption, and then part of this light will go through the sample. So that light which goes already through the sample will represent transmittance of the um, sample. So if we consider all together, reflection, absorption, and coefficient and transmittance as coefficients, which are defined in 100%, or we can consider it as unity. So unity is equal to reflectance plus absorption plus transmittance. So all together, according to conservation of energy, should give us unity. If we consider all these coefficients at any wavelengths, because they are obviously wavelength dependent parameters, they will give us unity because there is no other option for energy to dissipate. It's either reflected or absorbed inside the material or transmitted and just goes through the material and travels further. uh, so we mentioned that refractive index is always larger than unity for all materials, means that the speed of light inside the material is smaller than in vacuum. So what happens with wavelengths? We have here some graphical representation that when electromagnetic wave or light is traveling from one material to another, which is more optically dense, means that refractive index is larger than the refractive index of the first material. The wavelength is decreased. So wavelength lambda 1 is larger than lambda 2. Why frequency doesn't change? Only wavelength.
Due to conservation of energy.
Conservation of energy, we consider it as a flux of photons, so photons with given frequency, that is h nu, and in that case, we need to conserve energy no matter in which medium with which refractive index this wavelength is traveling. So this is general reminder of our previous discussions. And also there is one important principle, which is called hygiene's principle. We need to just provide some information on. So this principle is in the basement of development of all laws of geometric optics. And based on its concept, it's possible to describe the, for instance, like reflectance of light and show that indeed the reflected, the angle of the reflected ray will be equal to angle of the incident ray. So what is the standing behind this principle? So here this line is showing us a wavefront. So it's plane wave. Here we have spherical wave. So this wavefront is the geometric position of points with the same phase. The basic understanding of this Huygens principle comes from the assumption that any point of a wavefront can be considered as a source of spherical waves, like secondary spherical waves. So here we consider just 3 points, and these are just parts of these spherical waves which are emitted from each of these points. So here we can also pick up several points, and they create this secondary spherical waves. So if we know how fast light is traveling inside the material, so obviously we are talking here about some monochromatic light. If we know how fast light is traveling inside the material, then by drawing a tangential to this spherical secondary waves, here we get planar front, and here we get spherical front of the wave. We can predict position of the wavefront at any moment of time. So at any interval of time delta t, will define this distance, how far the secondary spherical wave will travel from the original point, and tangential to the line which is drawn along this secondary spherical waves will give us a position of wavefront at after time interval delta t. So that is the basic understanding of this principle, and today we proceed further with building images of objects, applying concepts of geometric optics. So let us focus first on this image where we have a flat mirror. We have some object O, some point object O, and consider how rays of light are traveling from this object towards the mirror. According to law of reflection, they are reflected from the flat mirror and observed by some external observer. So what appears to the external observer? That there is some image of this object O, which is located behind the mirror, and if we extend this reflected rays, they will converge in some point, which actually gives us the position of the image of this object. So there are several parameters which we need to know for our further quantitative analysis, and that is the position of the object with respect to the mirror. This is defined as P, and position of the image with respect to the mirror. So that is parameter Q. So there are two types of images. Objects are always just one type of objects. They are real objects. Imaginary objects, that's maybe when you have some hallucinations. But objects, we assume, are real, and images of the objects, they can be either real or imaginary. So what's your suggestion here? Do we have a real image or imaginary image? Okay, any justifications of your statements?
This is imaginary because it's behind the mirror.
So the definition between real and imaginary images of an object is when reflected rays, no matter how we consider them, do not or do directly pass through the image. So here we see that reflected rays, they are they're going away from the mirror, and they definitely don't pass the image position. So how we get image position, we actually extrapolate this reflected rays, and where these extrapolations converge, there we claim that we have some image. In this case, when reflected rays do not pass through the image, this is imaginary image. We will consider some examples later when reflected rays pass through the image point. In that case, we will deal with the real image. So now we have general understanding how this approach works with dealing for like some optical systems and building images. Images may be real or imaginary. Now let us consider the general approach of building the image of some extended object. So here we have just some point object, but usually objects possess some linear dimensions, and this is our extended object. So how we deal with that? So again, we pick up a single point of this extended object, and that will be this point at the top of the object. In order to get the image in optical system, when we have, for instance, flat mirror or any other mirror or a lens, we will consider them later. We need minimum two rays which originate from this point. So we pick up one ray which goes through the medium in between the object and the mirror, and the first ray goes parallel to horizon so that it hits the surface of the mirror at right angle. So, or at zero angle if we measure it with respect to the normal to the mirror. According to the law of reflection, what happens with this ray? It will be reflected, will travel exactly in the same orientation, parallel to the horizon, but in opposite direction. So that is the first ray. Second ray will hit the middle part of the mirror at some angle theta. Obviously, it will be reflected with the same angle theta. And now we have two reflected rays. What do we see here? This ray is going downwards, kind of, at angle theta. This ray is parallel. So they will never overlap in this side of the medium where object is located. So what we need to do then, we need to extrapolate these rays towards their interception at the point where the image of this tip of the object P will be located. So that is our position of this tip of the linear object, and the rest of the object will be located between this baseline and the top point. So that's how we get the image position and image building of system object flat mirror. And this concept will be applicable for all other cases also. Here again we have this distance P from the object to the mirror, distance Q from the mirror to the image. We need to keep in mind, if we have real image, something like here, this is some point object. We have two rays which are coming and reflected from the inner part of spherical mirror. These reflected rays go through the image position, the point where they intercept. So here we have real image. If we have imaginary and real image, the distance from the mirror to the image should be considered negative for imaginary object or imaginary image and positive for real image. So now, taking this all into account, we can proceed further because it's quite simple case and scenario when we have flat mirror. We have just imaginary image of an object and their linear dimensions are the same. So another important factor here that for flat mirror, image is always no, it's actually it's straight, so it's not flipped over. And this you will keep in mind because when we deal with other mirrors, in particular spherical mirror, we will see that it may be also flipped over, and this should be taken into account. So let us consider more complicated case, which is a spherical mirror. So what is spherical mirror? It's a segment of a sphere with some radius r, and it has some principal axis which goes through the center of this segment, and both sides of the mirror, the inner side or outer side, can be reflective. So we will consider reflection like building the image of an object via reflection from inner or outer side of these spherical mirrors. They have a little bit different results in terms of image formation. But this is the model system which we need to keep in mind. We have some radius of the curvature of this spherical mirror, and another important parameter is this principal axis. So how do we build the image of an object when we consider reflection from the inner part of a spherical mirror? So we have some object with height h. It is positioned with respect to the mirror at some distance p. So then what we need to do, we consider two rays originating from the top point of this object. What means originated? It could be either emitted when object is emitting light, or usually that's the most probable scenario, it's just reflecting. So we have some light source, it illuminates this object, and then there is some reflection of light from the top of the object. We consider the top of the object, but obviously we have reflection of light from all points of the object, and they are traveling, these rays of light are traveling towards the mirror. Yes?
So if we want to see the image, we should like place some paper at some the distance of q.
Oh, actually, you will see the image if you place an external observer like in this position next to the object and look on this mirror. So that's what you will actually see. This will be the image of the object. It will be smaller than the object itself and flip over. So
So is it like the length of the our arrow will be the same as the
so the if you consider the linear size of the object and image, so we will get the relationship which gives this ratio. So, but for the case when we have reflectance from the inner side of a spherical mirror, the image will be always smaller than, well, of course, need to keep in mind what will be the ratio between position of the object, radius of the spherical image. But let's say if we consider case like this, shown on this uh, figure, when position of the object is larger than the radius of the curvature of this spherical mirror, then the image will be always smaller than the object. It will be real image because now we have interception of reflected rays in the point of the image. So this will be real, smaller. Will be some magnification of this optical system in given condition smaller than unity, and it will be actually with sign minus, like negative sign. Why? Because the image is flipped over with respect to the object. But we will come to this point. Let us first explain how we form the image. So again, we pick up two rays which originate from the tip of the object. How we pick them up? So first, we pick up a ray. Let's consider this red ray, which goes through the center of the curvature of this spherical mirror. If it goes through the center of the curvature, then it hits the surface of the mirror at right angle. So means we have just reflection at the same direction in opposite way. So in this case, reflected ray will just come back to the point where it was originated at the tip of the object. Now we pick up another ray, which will be some blue ray, and this blue ray will hit the central part of the spherical mirror, internal part of the spherical mirror, at this point where principal axis is crossing the spherical mirror at the angle theta. So the reflected ray will also go at the angle theta. And now we see that reflected red ray and reflected blue ray intercept in this point, and that means this will be the real image of the tip of our object. So this is the real image of our object. Now we consider the large red triangular and yellow triangular. So the angle theta will be the same. So now tangent theta will be equal to h divided by p, and here will be h prime, the linear size of the image, but it will go with minus because it's positioned in the below the principal axis, and object is positioned above principal axis, so it goes with plus. This guy goes with minus h prime, divided by q, which is the distance from the image to the mirror. So taking this into account, let us write now the expression for the magnification. So we can write that magnification or maybe let's write first that tangent theta can be given as h divided by p, as we mentioned, and also tangent theta can be given as minus h prime divided by q. So from here, we can write that magnification, and magnification, that is the ratio of the image linear size divided by the linear size of the object. And oops, and that will be equal. What is this? Let me try to somehow try to doesn't want to work this time. Let me write this on the whiteboard, but what's going on? Okay, maybe here we can write tangent theta can be given as h over p or h prime over q. Yes. Oh, now use. Okay. Yeah, I don't know what's going on, but hopefully we can manage until the end. So now we keep in mind that here we have minus also because this h prime goes with the minus. From here we express the magnification, which is the ratio of the linear size of the image to linear size of the object, and that will be minus q over p. So the sign tells us if it's flipped or not. So negative means it's flipped image with respect to the object. Positive means that they are not flipped. So let us come back to the slide. So that is about magnification. Now we can consider other two angles, like two triangles with this angle alpha. So we consider the small red triangular and this blue or kind of greenish triangle. So when we consider them, we will be able to derive the expression for a so-called like equation for spherical mirror, which will give us relationship between the properties of the mirror, means the radius of the curvature, the position of the object P, and position of the image Q. So these three parameters, they are the most important in terms of determining the position and features of the image formed by spherical mirror. It will be true for reflection from the inner and outer side of the spherical mirror, so we can be applied for both cases. Just the signs of the Q, either it's real or imaginary image, that should be taken into account. Either it will be positive for real image like here on the slide, or it will be negative if we have some imaginary image, which we will consider um, when we deal with the reflection from the outer side of the spherical mirror. So now we consider this small red triangular and small green triangular. Let us come back to the whiteboard. And tangent alpha, that was about angle alpha, can be expressed from the small red triangular as h over p minus r, p position of the object, and r is the radius of the curvature. And the same tangent alpha from the small green triangular can be expressed as minus h prime over r minus q, where q is position of the real image with respect to the mirror. So now, taking this into account, we can consider absolute value for magnification, like h prime over h, and that will be r minus q divided by p minus r. We know that this magnification can be expressed as a ratio between q and p. So that's why we can write here that this will be equal to q over p. And now, after rearranging this relationship, we will get 1 over p plus 1 over q, and that will be equal to 2 divided by r. So this is the first form of the mirror equation. We will analyze it in more details next time, and eventually we'll write the more generalized form for this equation, which will be then applicable for not only even spherical mirrors, but for lenses also. But at this point, we stop with this equation. So we have three parameters. We have position of the object with respect to the mirror, position of the image, and radius of the curvature for the mirror. Obviously, if we have some spherical mirror, we know the curvature of the spherical mirror. We know where we are going to place our object, and that's why we can predict this parameter q, position of the image, with respect to the mirror, when we know two parameters, position of the object and curvature of the mirror. So that's important application of this mirror equation. Yes?
Should we put minus when we have q over?
No, we consider here absolute value, so we don't need the minus. So here we just want to know the absolute value. So let us summarize our discussion for today. We consider the principles which allow us to build optical images of objects when we have mirrors. So we started from a flat mirror, from easy case, but the principles, general principles, are always the same, no matter if it's flat or spherical mirror. So we need to pick up some point, usually it's the top point of the object, and then we consider two rays which are traveling from this point towards the mirror. Then, according to laws of reflection, they are reflected from this mirror, and we look where the reflected uh, rays intercept with each other. So if after reflection they intercept in this medium on the side where object is located, then we deal with the real image of the object in the point where this reflected rays intersect. We may have more rays. We may have 3, 4, 5 rays, as many as you want, at different angles hitting the mirror. But we need minimum 2 to see the point of interception, and that point will give us the location of the image. If we see that reflected rays do not intercept, they are going in different directions, then we need to extrapolate these rays in the side opposite from the side where object is located until they converge, they intercept with each other, their extrapolations converge in a point. That will be location of so-called imaginary image. So depending on the system, obviously, we need to consider its properties. If we have a spherical mirror, we need to deal with several factors. First of all, curvature of the spherical mirror, which is defined with radius, quantified with radius r. And also, we need to think from which surface, inner or outer surface of the spherical mirror, reflection will happen. So we considered so far reflection from the inner side of the mirror. We will continue next time discussion of this mirror equation. And then we will proceed further with the reflection from the outer side of the spherical mirror. Thank you very much for your attention and have a good day.